I just want to introduce myself. I'm George Rivera from EA Technology. I'm in charge of sales here at our New Jersey office. And with me is Bill Higginbotham, the president of our office in New Jersey. And our guest speaker is Dr. Brendan Englot from Stevens Institute of Technology. And we'll be starting here in a moment to talk about AI-powered robots for substation PD inspections. Before we turn it over to Dr. Englot, let me just give a little background on EA Technology and why PD is important while we're waiting for others to sign in and everything. Let me just start with a little bit about our company. EA Technology started out as a part of the British utility and then was privatized, and we became an independent company and started selling the products that were being made for homemade use, including handheld and full-time monitoring for partial discharge. We also do some consulting work, and we have offices around the world. In terms of partial discharge, why is it important and what is it? Let's take a look at a little example video here. You could see on this bracket, you could see the little sparks jump in the gap there. Sometimes it's visible to the naked eye. This is a little cell phone video. There's no instrument in this example here. What's really going on is that if you use this little diagram that we have here, and you see there's this green part which represents the insulation, and we have an air bubble inside, or it could be just under the surface or on the surface. It's the same effect, and you have an air gap there. And in a overall health type of instrument, maybe like a megometer or something, you go for a cable, you might not pick this up, or a thermal camera, since it's internal, might not generate enough heat. However, as the voltage goes up for the 50 or 60 hertz sine wave, you're going to reach a point where the spark's going to jump the gap, just like it's in the video that I showed you earlier. And every time that happens, twice per cycle, it's positive and the negative half cycle, it's going to eat away a very small amount, but still significant enough that over time you'll have a path, maybe not a straight line, but some path where you'll have a flashover event. And PD is a leading cause of substation failures in a variety of places. What we're mostly concerned with is medium and high voltage. So we say 3.3 kV and up. And then the rest of those bullets are just places where you would find medium and high voltage. There's a few different types of PD. There's corona discharge. This is like a sharp edge, like the threads of a bolt or a bracket that's in the electric field. Typically, you find it in an outdoor setting, and there's a lot of YouTube videos you can see, especially nighttime ones, where it's very visible. It's not so much of an issue for insulation, but it does create a lot of noise. And in an enclosure, there's some gases that are created if you have this occur in an enclosed cabinet where there's no air circulation. There's a reaction. It starts with ozone and ends with nitric acid that can create rust. You also have that rust with surface partial discharge, and you can see in that little photo there, there's a rust in the treeing and tracking that you might have, for those of you that have seen it before, might recognize. Surface partial discharge is the most common type of PD, and that's one of the areas that we're going to be talking about today. There is another type, or internal or void type discharge. That is an air bubble that's inside a solid piece of insulation. It could be a resin, like it's shown in the picture there, or it could be a porcelain insulator or some type of composite insulator where you have some delamination occurring due to thermal stresses or some other issue, and an air bubble is forming. Because it's inside a solid, the the typical techniques of detection are not usable, so we have other techniques for that. For ultrasonics or acoustic sensing, this is what we would use for surface PD, and it could also detect corona. And so here's an example, switchgear type of example. There's data that can be collected. I'm not going to get into interpreting the graph that's there, but you can have a sound clip that sounds so you'll see folks wearing headsets when they're doing acoustic inspections. They're listening for a crackling sound similar to a frying pan sound. And there's data that can be collected and plotted for that. Not only on the front side of a switchgear compartment, you can also have it in the cable compartment. You can see in this example, it's detectable by ultrasonics. The treeing and tracking you can see in the pictures there. The internal partial discharge, so going back to that example with the air bubble in this cast resin current transformer example, is more difficult because the sound has to travel through a solid. And so one of the things that EA is known for is back in the 70s, we discovered and developed the first sensors for a different technique, which was then named transient earth voltage, or TEV, and now it's used by a number of companies worldwide, not just us. So in this example here, we have a piece of bus duct, and there's the red bus bar that's there, and it's got the 3 supports there. They're supposed to be insulators, but let's say the middle one has an air bubble. So the sound, if you're outside the cabinet, you're not going to be able to pick it up with those acoustic or ultrasonic sensors very well, or if at all. So what we discovered was there's also another effect, a high frequency current pulse that's depicted by that light blue line there. I'm not sure if my mouse is visible, but that high frequency current pulse, it rides on the metal on the inside, and it's looking for a path to ground. And in this example, it finds it through this joint or gasket here and makes its way to the outside. Now, it's not harmful to touch the panel from outside, but with the right sensor, which is what we developed back in the 70s and now have perfected, we have something that can be detected. And so a typical inspection will include, as a minimum, an acoustic or ultrasonic inspection and then a TEV test. And we're looking for 2 different sets of problems. All right, so with that background, let me properly introduce Dr. Brendan Englot. He's the Associate Professor of Mechanical Engineering at Stevens Institute of Technology in New Jersey, and he's also the Director of the Stevens Institute of Artificial Intelligence. And they've been doing, I'm an alumni, and I've been getting the alumni newsletter, and I find out that they're doing some work in our field here in substation work. I was able to work out an arrangement here to have him present a little bit of his findings of the research. Not only is he associate professor and director, he has several degrees from MIT, including a Ph.D., and he's worked on doing underwater robot inspections for the Navy and Coast Guard with MIT, and he's also worked with the United Technologies Research Center in Connecticut, where he was a research scientist and principal investigator in autonomous and intelligent robotics laboratory, and a technical contributor to the Sikorsky Autonomous Research Aircraft. And he's been with Stevens since 2014. So let me turn it over to you, Brendan. Thank you so much for making yourself available and doing this presentation. And if folks, if you have any questions, if you can put them into the chat, we'll try to address them at the end.
Thanks, George. My pleasure. And shall I be asking you to drive the slides as we go through the presentation?
No, let you
Yeah,
do that. So yep. So you should. I just have the one slide there,
okay.
your cover slide.
Switch screens here. There we go. Okay. And you'll all have to forgive me. Someone's mowing the grass outside, so my dog is barking occasionally. I'll try to mute myself if it gets too disruptive. But I'm thrilled to talk to you about this project to develop a very special mobile robot, what we call a mobile manipulation robot for partial discharge inspections in indoor distribution substations. Before we get into the details, though, I wanted to tell you a little bit about our organization at Stevens. So Stevens Institute of Technology is based in Hoboken, New Jersey. Stevens Institute for Artificial Intelligence is one of our newer faculty research centers. The goal is to kind of bring together the faculty at Stevens across all the different departments and schools, since so many of us are studying AI, using it in our research and our teaching, and it's having such an impact across all disciplines of science and engineering and beyond. And so we have 100 faculty at Stevens now that belong to our AI Institute. We have 9 different focus areas that you could see are quite wide-ranging. And my home department is actually the mechanical engineering department at Stevens, and we have quite a few faculty in our mechanical engineering department who are members of our AI Institute. Many of us are robotics researchers like myself, where I work at the intersection of AI and robotics. Some are using AI for engineering design. So it's definitely an exciting time to be at Stevens. A lot of exciting things happening in AI. And I'll just note that we recently, earlier in this academic year, had a big relaunch and open house of our AI Institute, kind of celebrating the grand opening of our physical space that we have there in the Gateway Academic Center. And we had a lot of exciting projects on display. Just to give you an idea of the breadth of activities that are going on right now in our AI Institute, we had a guest speaker, Manuela Veloso, who is the head of AI research for JP Morgan Chase. We had a faculty member demonstrating his augmented reality Rubik's Cube solver that he developed for a DARPA program, where it instructs the user how to manipulate the Rubik's Cube as you're holding it in your hand and viewing it with the camera. And a professor from our humanities school, Christopher Manzione, debuted an AI-generated short film that generated both the text, the images, and the music, all using generative AI. So that was a good representation of all the exciting things going on in AI at Stevens. I'll also just tell you a little bit briefly about my research lab at Stevens, which we call the Robust Field Autonomy Lab. And one reason we give it that name is because we focus on an area of robotics called field robotics. Robotics intended to work outdoors in the real world in harsh conditions with often degraded sensing and communications. So today you're going to hear a lot about this special robot that we developed for partial discharge inspections in indoor distribution substations. But that is just one of several robots that we use in our lab and in our research. We also, the ground vehicle that is part of this robot also is used for a lot of other field robotics applications, including in multi-robot systems and distributed autonomy. And then we also do a lot of work with underwater robotics, one of the most challenging types of field robotic systems where sensing and communication are often really challenging. And we're trying to develop new navigation algorithms that could help all of these robots operate more reliably out in the field. And so that takes me to this specific application that I'm going to focus on today. And just to provide some background context, this is a problem that we began looking at in collaboration with Con Edison in 2021. It was very early in 2021 that we started this project. And the goal was to try to keep humans out of harm's way. You know, we just heard George talking about some of the dangers associated with partial discharge. Substations might, you know, there might be fires, there might be explosions that put substation personnel at risk. And so if we could have a robotic system, kind of serve as the first line of defense, performing regular diagnostic inspections, hopefully it would increase safety, and it would also just increase the general monitoring of the condition of the many, many substations that require this type of inspection. So as a test case for a representative robot substation inspector, we looked specifically at pothead compartments within distribution substations, and the goal was actually to perform the exact two types of PD sensing that George was talking about, TEV, the transient earth voltage, and to collect an acoustic measurement from the air vent on the door of the pothead compartment cabinet. And so those measurements are performed using a handheld sensor, designed for humans. So in our case, we developed a robot that could manipulate and use that same handheld sensor. And one of the challenges that we're going to address here is kind of the two constraints that are somewhat in opposition to one another, that we needed this robot to be able to drive through narrow clearance areas in order to access all the areas of the substation required, narrow enough to fit through kind of a single width doorway, or perhaps even a narrower passage than that if a corridor is obstructed. And then on top of that, for it to be able to access tough to reach measurement locations, ideally reaching as high as possible. So we wanted a robot small in size, but with high reach capability. So first I'll talk about the ground vehicle that kind of serves as the base for this robotic platform that we developed. So we're working with an electric research robot called the Jackal. It's a research robot made by a company in Canada, ClearPath Robotics. They make a lot of robots that are used by universities and in industry to develop and prototype new autonomy capabilities. And here you see this robot doing what it does best, which is using its LiDAR. In this case, it's equipped with a 16-channel Velodyne puck LiDAR, one of the types of LiDAR you often see on self-driving car prototypes. This just has a single one. It has 16 beams that span 30 degrees in the vertical, and it can see out to 100 meters. So you can actually see the beam returns here as this robot drives around an example distribution substation, and all of the beam returns are color-coded based on their height. So everything on the floor is coming back red. Everything, up the walls and looking at all of the switchgear cubicles are coming out in colors spanning from green to purple. And so what you see here actually is a very reliable scan matching capability that this robot uses in order to track its trajectory inside a substation. Since we're indoors, we don't have GPS, we don't have an absolute position reference inside the substation. And one of the most important fundamental questions we have to answer is, where am I? Where is the robot located in the substation? So what you see in cyan there is the estimated trajectory of the robot purely based on scan matching. And the way that the scan matching process works is it takes the current live point cloud generated by the robot's LiDAR, and it matches that against the white reference point cloud that you see in the background. So there is, at every instant a new scan arrives, 10 times a second. So in every 10th of a second, that new scan is matched against the reference map using an algorithm that's pretty widely used in robotics called ICP, Iterative Closest Point, which is just basically an iterative point cloud matching algorithm that, given an initial guess of the robot's location, initializes that point cloud against the map, and then we just try to match the two together as closely as we can. And you can see that in an environment like this one, where there are not too many other dynamic objects, it's pretty robust. And if you look at it closely, you can actually kind of see a bunch of people walking around following the robot behind. There are a bunch of signatures in the wake of the robot. So we're all gathered behind this robot, maybe 3 or 4 people walking behind it as it drives through the substation. And the point cloud matching process is robust enough that all of that background noise, all of us gathered around it, are not interfering with its ability to match its scans against that white point cloud that was generated on a previous visit to the substation several weeks prior. So all of that is achieved using a software architecture that is fairly standard in mobile robotic systems for GPS-denied robots that are using a range sensor like a LiDAR to navigate. There actually are quite a few open source software packages that we integrated together to achieve this. So it is a custom integration, so the architecture is unique to us, but the individual modules are not. These are all algorithmic modules that are widely used by researchers in robotics, and they're all free. In fact, one enabler of that is our use of a framework called ROS, the Robot Operating System. This framework is widely used by robotics researchers around the world. And basically what it provides is a easy to start from and very easy to customize communication infrastructure for robotic systems. And a lot of kind of the key algorithms supporting robot navigation and communication are implemented in Python and in C++. So we rely on a few different algorithms, the ICP scan matching algorithm that I mentioned to you before. Then sometimes on top of that, we employ another algorithm called SLAM, simultaneous localization and mapping, that also allows us to build maps as the robot drives through the environment. We keep track of the waypoints that are part of the robot's inspection mission, and those are repeatedly monitored and published as the robot reaches its waypoint. And then there is the automated path planning of the robot, which lives inside this routine called MoveBase. This is part of ROS's navigation stack. And as you can see, it involves just more than a single path planner. In fact, to navigate really reliably in a substation environment like the one you saw on the previous slide, you need a global planner that will kind of set waypoints for the vehicle that might be quite far away. And then you have to track your progress to those waypoints and perhaps make planned revisions if the robot gets stuck, if a corridor becomes obstructed, if an obstacle appears that was not originally in the map. And so that's why we also have a local planner that works in conjunction with the global planner. And so all of these things together allow a user to issue a waypoint or to have in advance a mission that might have several waypoints at pothead compartments in the substation that you wish to inspect. And those waypoints will all be visited by the robot autonomously using this navigation architecture. So I'm just going to show you another video clip of our process for kind of testing that. So in the earlier movie clip you saw, we were manually piloting the robot. We were teleoperating it and telling it exactly where to go. But now what you see, this is a clip of us testing the robot in our laboratory at Stevens. And we're basically setting waypoints for it one by one in kind of this ring shape, going outside of our lab is located here, and it goes outside, drives through this much larger educational lab space sitting outside our door. And we're testing the repeatability of this process, just ensuring that if the robot goes through this route 5 times in a row, it's basically tracing out the same path every time. And so for us, this was kind of an important validation process to ensure that when we issue waypoints for the robot, it can drive to them with precision and repeatability. And again, I'll just note the robustness of the scan matching framework that all of this relies upon, because right now, the live LiDAR scans that you see here in red and orange, and again, color is just an indicator of height. All of those LiDAR scans are being matched against the white reference point cloud that you see in the background. So this is a highly dynamic environment. There are students walking through this space continuously. The environment's full of chairs. People are pushing chairs and moving them in different locations. And despite all of that, and you can kind of see that clutter, if you look carefully at the LiDAR scans, you'll see signatures from people, from furniture that are not part of the white reference point cloud. Despite all that, this process works remarkably well and allows the robot to localize using that prior reference point cloud. So now I'll talk a little bit about how we took that Jackal ground robot and enhanced it with everything that it needed to perform PD sensing in a distribution substation. So the biggest challenge was, once we knew the base that we wanted to work with, we knew that this would be narrow enough to fit through the low clearance areas required. How do we reach as high as possible and do so in a safe and stable manner? And so looking at a wide number of possible manipulation solutions, we ended up choosing a Canova Gen 3 6 degree of freedom arm to integrate into the Jackal robot. And this required some careful thought and planning. You cannot buy this integration off the shelf. And one of the reasons why is because most vendors would not be eager to sell you an arm this large on top of a robot base this small. So in order to get that combination to work safely, we had to think very carefully about where we mounted the base. We also had to make sure that any time the robot is driving around, that the arm remains as low to the ground as possible. So it collapses down into this, what we call travel configuration, and it only moves around when the arm is collapsed in this way. You can also see that in addition to the LiDAR that the ground vehicle base was using for navigation, this robot actually also has kind of a open wrist where we can, the interface where we can connect custom, what we call end effectors. Whatever goes on the end of a manipulator arm, we call that the end effector. It could be a gripper. It could be, in our case, a handheld PD sensor. And then right at the end of the wrist, we have a what we might call an RGBD camera or a depth camera. So this is just a monocular color camera, but then in addition to color, we also have the depth information of every pixel because there's an infrared range sensor next to the color camera. So this is a very useful sensor for kind of sensing the workspace around the tip of the arm. So to perform that custom integration, I guess a lot of thought and care went into the power and networking associated with that, because this system really is composed of two completely separate robots. So we have the the Jackal ground vehicle, and then that has its own onboard computer. Basically, all the computers and networking equipment involved are shown in purple here. So the Jackal ground vehicle has its own computer. The ARM also has its own computer. We used a small Intel NUC industrial computer to run the ARM. And so basically two different robots, two different computers, two different sets of sensors. The ground vehicle was using its own LiDAR, and the ARM and its computer were using the wrist camera, as well as sensors in all the joints of the arm as well, and the interface to whatever we place at the tip of the arm. So all of these had to be powered and integrated. We basically had to set up a network inside our robot so that the two robots could communicate with one another and pass messages to one another. But each is running its own processes independently, and those processes share the necessary information for the two robots to work together to execute the substation inspection. And then we also, whenever we're testing this robot, we're monitoring it with a laptop. The Jackal ground vehicle does have Wi-Fi, and although these have a wired connection between them, the ARM and the ground vehicle, we have a wireless connection to our laptop. And that just allows us to stream some of the data, not all of it, but just a small enough amount of data that we can make sure the robot is performing as intended. And we can watch those key messages on our own laptop. So this is just an overview of all of those components that played a role in this integration. So everything you see highlighted on this slide was a custom installed component of that integration. And that included the need, as I mentioned, to power everything, to step up or step down voltage in certain instances, to physically and in a structurally sound manner mount the Canova arm to our vehicle, to place an emergency e-stop switch so that we could shut the vehicle off if anything unexpected happens. And also, this is the Intel NUC computer that runs the arm. So this is actually flipped upside down here. When the robot's actually operated, this whole panel is upside down, and the Intel NUC computer is just tucked down here. So down here is the computer that powers the arm. So getting all this into a compact package took a lot of careful planning and design on the part of our team of students. So getting all of this fully integrated then allowed us to kind of examine the fitness of this robot to actually perform a substation inspection and not just drive around autonomously, but also physically interact with the substation switchgear. And so one key consideration in that was where to place the arm relative to the LiDAR. We actually have the LiDAR kind of on the nose of the vehicle and the arm sitting behind it. So with the arm mounted, we kind of lose a part of our visibility here. So this rear chunk of the LiDAR field of view is obstructed by the arm. We tried to minimize that to the extent possible, and after some testing, we determined that this is still a pretty safe and wide-ranging field of view for autonomous navigation. And so moving toward an autonomous substation inspection, we had to kind of develop our own autonomy architecture for this. And as we were discussing earlier, and as George was discussing, two of the key measurements for PD inspection are TEV, taking the transient earth voltage measurement, where we were working with a handheld sensor that had to make physical contact with the outer panel of a pothead compartment. We had to take an acoustic sample from the air vents of the panel of the pothead compartment. And then we also just had to visually identify the exact compartment that we were inspecting, which required us to visually detect a barcode placed on each of those compartments. And upon scanning that, we were able to collect the other two diagnostic measurements. And so in order to do all of that autonomously, we had a whole series of behaviors that was kind of programmed into our robot that was composed of two key steps. So the first of those steps was the robot actually had to drive to the correct location once it got to the correct waypoint in front of the pothead compartment in the substation that it needed to inspect. Then it also had to kind of align itself with the panel close enough that it was able to reach up and actually begin taking these diagnostic measurements, which require physical contact with the panel. And so to do that, we had kind of a parallel parking procedure where the robot would drive down the aisle of the substation, reach the cabinet that it wishes to inspect. It would turn to face the cabinet. It would then drive forward and align itself. And then once it was properly aligned with respect to the vehicle, it would then reach up with its arm and then also use the depth camera on the tip of the arm to ensure that the arm was properly aligned with the panel to begin making physical contact. And then the joints of the arm also had their own onboard torque sensors that allowed us to determine that physical contact had been made. So we ran a few experiments to test the precision and the accuracy of this parallel parking procedure. We had this automated behavior that would allow the robot to, as I mentioned, drive alongside the panel, then turn, drive toward it, and align itself in both X and Y. And over the course of 100 trials, we found that there was a pretty acceptable standard deviation associated with this process, just about 2 centimeters. So there was a little variability associated with this process because the robot's using its LiDAR to do this, then it's using the camera on the tip of its arm to do this. And those two processes give us a standard deviation of about 2 centimeters. But that was still more than enough. It was within the envelope of error that was completely acceptable to allow us to identify the key locations to take our measurements. So now I'll just show you kind of a few frames of that panel alignment process where, in this case, we're just pretending that the door to our lab is the panel that we want to collect the measurements from. So the robot drives along. Once it knows that it's gotten far enough in the forward direction, it turns, then it begins to drive toward the panel. It gets to an acceptable standoff distance, which it verifies using its LiDAR. And so once the LiDAR tells it that it's close enough to the panel, then it kind of deploys the arm. The arm also looks at the panel, and the depth camera equipped at the wrist of the arm is used to make sure that the robot is appropriately aligned. And if any adjustments are needed, we can kind of abort this procedure and repeat it, and the robot will make those adjustments again. Or we may just make some fine adjustments with the arm itself, because the arm is able to swivel at the base. And so those two types of corrections allow us to align very accurately with the panel so that we can take the diagnostic measurements. Okay, and so on top of that, we are actually gripping and operating a handheld PD sensor. So we had to build a custom electromechanical interface for that sensor so that we could use it to collect these measurements. And so what was earlier, you might recall, just a blank face at the wrist of the arm, we use that interface, which is both kind of a mechanical and electrical interface, to basically build a custom cup holder, you know, an electromechanical cup holder for the handheld PD sensor, which gets inserted into this sleeve here. And depending on the needs, we actually have some servo motors built into the wrist that can be used to physically press buttons on the sensor if necessary. Although we don't power or electronically connect to the sensor in this instance, this interface could be modified to do that if necessary. Right now, we actually do power these servo motors from the arm itself. So the arm is being used to control any physical button pressing on the sensor that might be needed. And so this wrist interface has its own little Arduino microcontroller inside to control that process if that's needed. So putting all of those things together, we also needed to find a reliable motion controller for the arm. And so there are a few off-the-shelf software libraries that are used for manipulator arm control. This is a widely studied area in the robotics field. Working with high precision with a robot manipulator arm to perform complex tasks is one of the most widely studied problems in robotics. And so we had two candidate motion controllers that we wanted to test. One was made available through a framework called MoveIt, which is widely used. But we found just using that controller off the shelf to drive the arm to the desired location to collect measurements had a rather low precision associated with it. So trying to deploy the arm under a lot of different parameterizations of both the controller and the computer vision algorithms that were being used to identify key targets on the pothead compartment panel, we had although there were some algorithms that failed outright just due to how the computer vision was parameterized, we still had a lot of variability in terms of the deployment of this controller, where you can see there's kind of a range of about 4 centimeters here in terms of where the arm will actually end up making contact with the panel. So being within that kind of 4 centimeter diameter sphere was a little too much error. So we moved on to a different controller that was made available actually through the specific arm we were working with, the Kinova Gen 3 ARMS API for users of Kinova ARM platforms. And we were able to, using that controller, get the error down to a much more acceptable level, where here, again, trying to deploy the arm to make contact with desired measurement locations on a pothead compartment panel, we encountered much higher levels of precision, and that 4 centimeter diameter kind of circle of uncertainty now shrinks down to just a centimeter or 2. So our ability to deploy the arm and have it make contact with the desired physical location now has this high repeatability within about a centimeter or so. And this just compares those, zooms in and kind of compares the reliability of the two different ARM controllers that we were considering. One of the things, calling this a controller might even be it might hide a little bit some of the complexity running under the hood, because this system also has to plan for the geometry of the arm. So it takes into account the different lengths of their arm, the coordinate frames connecting them. It ensures that any motion or trajectory taken by the arm has no possibility of self-collision. So there is some motion planning involved to ensure that the arm trajectory is collision-free. But then also, because there is computer vision in the loop, there is the potential for some error to be introduced into this process. So we were able to hit our target much more reliably using the controller we chose to adopt. So putting all those things together, I now have a video clip showing you the entire inspection process from start to finish. And I know there might be a little bit of latency in this clip, but I'll let it play a few times and you can see the whole process from beginning to end. So the robot is pretending that these two doors in our lab are the pothead compartments that it's tasked with inspecting. So all that it knows in advance is the waypoint locations of the two doors. And it got to the first one here, it aligned itself, it drove close enough to make contact. It had to scan a barcode in order to start its measurement process. It then given some knowledge in advance of where the vents are to take acoustic measurements, reaches to that location and takes an acoustic sample. And then it also makes physical contact with the door to collect a TEV measurement, which actually you see happening right there. That was the physical contact. And it uses its onboard torque sensors to ensure the contact was made. Then it drives itself over to the second measurement location. So this is another door. We told it that this is a pothead compartment as well. So now the robot reaches the door location. It drives close enough that it can make contact. It turns again, so the arm is aligned. Then the arm itself also makes a few adjustments. Then it identifies and scans a barcode, and then it begins collecting the diagnostic measurements. So first it takes the TEV measurement, which requires it to make physical contact with the panel, scans the barcode again, gets a little bit closer, then it collects the acoustic measurement. And then it collapses back down into the travel configuration. So I'll let this whole video clip play one more time now that you're kind of oriented a little bit in terms of what we're testing here in this mock-up of a substation. So again, the robot approaches this first door, collects that barcode scan measurement, collects an acoustic sample, scans the barcode again, makes physical contact to collect the TEV measurement, then it collapses back down into its travel configuration after identifying the barcode one last time. I think in this case, it actually repeats the TEV measurement. Took it from 2 different locations, and now it collapses back down into the travel configuration and drives to its next waypoint. So as the robot is performing all of these steps, and you kind of see the video of that on the left, on the right, you actually see the data products that the robot itself is using to do all of this, because all of this is being done fully autonomously. The only thing it knows in advance are the locations of the pothead compartments where it needs to take these measurements. And then also on the door of the pothead compartment cabinet, it knows where the key locations are that it should be taking the acoustic and TEV measurements. And the barcode that you see it detecting occasionally, it's actually searching for that actively using its camera. And then once it gets identified using the camera, it then drives in to scan that barcode. So everything that you see on the right helps to support that autonomous navigation process. So the light-colored points that you kind of see in the background everywhere, these are the reference point cloud that the robot's using to match its LiDAR data against. The live LiDAR data is what you see in color, the red LiDAR beams on the floor, and the green ones at the top of the ceiling. The color just indicates the height of the LiDAR returns. So you can see that LiDAR scan gives the robot a pretty clear idea of all the obstacles in the environment, and it's actively using that LiDAR data and matching it against the reference point cloud shown in the background here. That scan matching process is helping the robot localize itself. And that's the basis for this cyan-colored trajectory estimate. So the robot's estimating its trajectory here using that LiDAR scan matching process. And the new thing you see here, now that we're using this arm, is this purple patch shown here. So this purple patch, and I'll show it to you again once the robot gets to its next inspection destination. So the robot drives to the next door to perform the next sequence of measurements. As it turns, here you'll see it once again. This purple patch is the depth data from the wrist-mounted RGBD camera. So that data is also very important, and you can see when the robot's close enough to the desired inspection location, it basically is just a rectangular-shaped plane. And so we fit a plane to the data in that return point cloud. And we use that to determine the robot's orientation relative to that plane. We assume that the surface of the pothead compartment cabinet is planar, and then the robot actually is steering itself and actively making corrections based on its estimate of where that plane is located. So two very important navigation sensors are being used together to drive this process: the LiDAR on board the vehicle, and then the wrist camera up here, which has both color and depth information. So the color camera is being used for target detection on the pothead compartment panel. The depth sensing is being used to align the arm properly to the panel, and the LiDAR is just being used for general autonomous navigation of the vehicle platform. So putting all of those sensors together, we were able to achieve a pretty reliable autonomous navigation capability. Over the course of working on this project, it actually also was the subject of a Ph.D. thesis at Stevens. So Eric Pearson was the Ph.D. student who was the technical lead on this project, and he just graduated a few months ago. He's now working for a small robotics startup company based in New York City, and this work was the basis for all of the research publications that supported his doctoral thesis work. And this work was generously supported by Con Edison. And I'll just close by showing you one last picture of us testing this robot inside a real Con Edison substation. I didn't show you the data and the imagery from inside the substation in the interest of confidentiality. I just showed the example running in our lab. But we did have the opportunity to test this robot in real substations, and it worked in very much the same way. We gave it the waypoints where the pothead compartments were located, and the robot visited one after the other and performed that series of automated measurement steps. So it was a great opportunity to support the work of a bunch of students at Stevens, and also to tackle a real-world problem that was a very challenging robotics problem. So hopefully, with the time we have left, I would be happy to take any questions that you have.
Yeah, we have a few. Some of these, I think, as you went through the presentation, might have got answered already, but maybe you want to elaborate on them. I'm going to go in the order, that way it makes sense as far as the flow of your presentation. So the first one is the map or localization done in full 3D or just 2D?
Yeah, that's a great question. So I can confirm it is done in full 3D. Even though this robot only drives on flat surfaces, that's the most that a robot of this design can handle, we found that the full 3D just allowed us to have a more robust scan matching process, where even if we had a lot of clutter, a lot of dynamics in the environment, people walking around, furniture getting moved, the general three-dimensional structure of the environment we were in, the building, the walls, the corridors, that really helped us register these the LiDAR scans robustly. So doing it in 3D was very helpful, I think.
So this one is, do you receive the actual measurement data for analysis? And yeah, it's stored on the memory of the handheld, correct?
That's correct, yeah. And in our case, Con Edison was evaluating a few potential handheld sensors. We were trying to design a robot that could accommodate the general usage of them, through this handheld sleeve that we developed. But we did not have a physical interface to the sensor that was that allowed us to obtain the data on our robot. So everything just got recorded on the sensor and could then be analyzed later. But that is something that could be a future capability of this robot if we were able to electronically interface with the sensor.
One of the folks that's more of an electrical engineer in the audience wanted to clarify your use of the term pothead. He gave a long answer. The short version is that term is mostly for outdoor cable termination connections. For indoor, like it's in the picture here, just saying switchgear, panel, cabinets, I think that's more commonly used than for
good
people
to know.
And
our focus on those was at the request of the sponsor. I guess, within their substations, that was
their terminology.
A specific terminology used to refer to some switchgear cubicles rather than others. And I think based on the lines that were coming into those cubicles, and they were labeled pothead compartments, so we had to look for ones that had the signage that said pothead compartment. those were the ones associated with higher rates of failure. So I think they wanted us to focus on that particular type of switchgear because of the the potential for fires or explosions in the failure scenarios that you were discussing earlier.
Do you have to be in the room to control or watch the robot, or?
Yeah, so everything you saw in the video, our presence in the room there was completely optional. So no intervention was happening. Actually, what you see here in this, so when we do wish to manually control a robot, we have this PlayStation controller that we can use to manually teleoperate it. But when the robot is doing what you saw it doing in that earlier video, it is completely autonomous and required no human intervention. So we're just watching it for the purpose of safety. We were streaming some of the data on our laptop just to monitor its performance, but we would not need to be in the room.
Now, I heard you mention, there was a question about the ports. So for the acoustic measurement, you mentioned that there's, in this particular switchgear lineup, there's vents, and so that's where you were picking up the acoustic measurement?
Correct, yeah.
Okay.
And they're not always in the same location, but we assumed that in a given substation where this vehicle would be operating, most of the switchgear of interest had similar panels. The vents were in similar locations. So in all likelihood, this robot would have to be programmed for the layout of a specific substation. But in all of our use cases, the vents were usually in the same part of the same location on each panel.
Okay. Are the robots' computers EMP shielded?
Good question.
Or can they be?
I don't think they are. That was not one of the considerations in developing this prototype, but that is an interesting suggestion. I think there's a lot of interest in trying to begin a phase 2 of this project, where one of the limitations of this robot is that it still does not reach high enough to perform the full set of diagnostic measurements desired. So as we try perhaps building a new version of this that could reach even higher, that might be an important consideration if we really want this to be reliable in the field.
Okay. There's a question about this doing trials or further research. I was going to discuss that later, but certainly everyone will have our contact information. In fact, I can present. Yep, you should see our contact information there. Anybody watching on YouTube, it'll be on our YouTube page as well. They can reach out to me, and I'll pass along anything and get Dr. Englot involved if you want to pursue some type of trial or research. There's a lot of variability with the arm and the type of wheeled mobile robot and other things that can be discussed. Can the robot be remotely monitored and supervised? I believe you answered that, but if you want to elaborate any further.
Yeah. So everything on the robot is broadcast over Wi-Fi. So as long as there's a wireless network that we can connect to, the monitoring of that data does not have to be on site. We were always nearby, connected to the same network, monitoring it on our laptops. But as long as that robot is connected to a wireless network, you could monitor that data remotely as well.
Okay. So look, I got to lean in here. You mentioned that the full 3D localization was able to sort out clutter during the localization phase. Was there any special processing needed to be done to the reference point cloud to enable this? Or did you need to make sure that the point cloud collected for the reference was cleaner than expected in the runtime environment?
Yeah, that's a great question. So yes, just to allow the system to be as robust as possible, and because that reference point cloud is going to be used a lot. We did invest some time to try to clean it up a bit, so if there were obvious objects in the point cloud that were dynamic, people, for example, we did manually crop any people captured in the scene out of that reference point cloud just to make it a little cleaner, since we knew there would never be a person standing in that place again during a live experiment. So yeah, a little bit of processing was invested.
So the map making was done. It's really someone physically has to be there and watch what's going on. It's not done autonomously.
Correct. But the nice thing is it can be done once and only once. And to just give an example of that, so where you all saw us standing in that photo at the end of the presentation, we collected one reference point cloud there in 2021, and we used it for the entire duration of our experiments through the end of 2023. Even though there were a lot of things changing in that environment, there would be carts pushed around, boxes here or there, rack out breakers removed from switchgear cubicles and relocated to various places. Despite all that, the same reference point cloud worked for several years. Okay,
well that's the end of the questions, and we're about 1 hour in. I'm sure if you guys have any further questions, please reach out to our our sales email. I'm the person that checks those, and for your time, thank you so much, Brendan. I appreciate it. It's really interesting, and it's kind of a lot of fun to see that progress. And I think it's important. You see AI and robotics; it's all over the news. But to see it, being applied in our portion of the world, in our little industry, is kind of fun, and hopefully will be of value to some folks.
Thanks. Great speaking with you all.
Yep. Thanks everyone for attending.